Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone. Thank you for joining and welcome to the final stop of the 2025 session of the Quantum World Tour. My name is Sierra Shukair, and I will guide and moderate today's session. Before we begin, I want to speak briefly to the purpose of the Quantum World Tour for those who are new to the tour itself. Throughout this year, we have traveled virtually across national ecosystems to build a clearer, shared understanding of how quantum technologies are evolving around the world. Each stop has reinforced the same principle. Visibility in science is a foundation for global collaboration and responsible development. Today's episode highlights that exact scientific progress in Russia. The focus of this episode is to speak to the science itself, the research directions, the technical achievements, and the areas of ongoing work. The Russian scientific community has a very long-standing history in physics and quantum research, and the speakers joining us today will present developments across computing, communications, and sensing that contribute to the broader global landscape. We will begin the session with welcome remarks from the Russian Academy of Sciences, the Ministry of Science and Higher Education of the Russian Federation, and the Ministry of Digital Development, Communications, and Mass Media of the Russian Federation, and the Deputy Permanent Representative of the Russian Federation to the United States Office in Geneva. We will then proceed into a detailed exploration of the national quantum strategy and scientific achievements, followed by perspectives from both industry, including startups, and then we'll finally take a look at education and workforce. Thank you for being with us in this very timely and important conversation. And with that, it is my pleasure to hand the floor over to our speakers for the welcome remarks.
According to the schedule, yes. Dear colleagues, dear participants of the webinar, my name is Alexander Gorbatsevich, and I am academician of Russian Academy of Sciences and vice chairman of Scientific Council of Russian Academy of Sciences on Quantum Technologies. This council is headed by President of Russian Academy of Science, Gennady Krasnikov, and is responsible for expertise in this field in the Russian Federation. First of all, I would like to deliver a welcome speech, welcome address from the Vice President of the Russian Academy of Science, academician Vladislav Panchenko. Dear colleagues, on behalf of the Russian Academy of Sciences, I am pleased to welcome the participants of the joint webinar of the Russian Academy of Science and the International Telecommunication Union Quantum World Tour, Russia. The government of our country pays great attention to the development of quantum technologies, which, without exaggeration, are one of the most breakthrough and promising areas of modern science and technology. Starting in 2019, Russia has been successfully implementing roadmaps recently extended until 2030 for the development of two high-tech areas, quantum computing and quantum communications. Currently, active work is underway to launch a comprehensive research program in the field of quantum sensors. I would like to emphasize that the Russian Academy of Sciences make a great contribution to the development of these areas, primarily at the level of fundamental and exploratory research. Quantum technologies are, of course, an interdisciplinary field of science and technology that unites scientists, engineers, technologists at different stages of research and development. Successful development of quantum technologies is impossible without the active participation of industrial partners following the relevant the relevant market segments. In addition, the future of quantum technologies is largely determined by the training of new specialists, which requires close cooperation between universities, academic institutions, and industrial partners. All these aspects are discussed today at the joint webinar. I am sure that its program will allow to gain a complete understanding of the development of quantum technologies in the Russian Federation. Our webinar is particularly relevant due to the fact that 2025 has been declared the International Year of Quantum Science and Technology by the United Nations, which underlines the global importance of this topic. I wish the webinar participants fruitful work, further success, and strengthening of cooperation. Vice President of Russian Academy of Science, Academician of Russian Academy of Science, Vladislav Panchenko. Thank you.
Thank you, Mr. Alexander, for those brief remarks. And now we're going to hand it over to Mr. Shoytov for additional remarks.
Добрый день, уважаемые коллеги. Я по-русски буду выступать. Этот год официально провозглашен Генеральной Ассамблеей ООН Международным годом квантовой науки и технологий, что подчеркивает их растущую роль в решении глобальных задач. Современные изыскания в этой области служат катализатором прогресса для множества сфер, от здравоохранения и экономики до новых инженерных решений. Учитывая стратегический вес этих разработок для цифровизации стран, укрепления их национальной безопасности, практически все развитые государства уже запустили национальные квантовые программы, где ключевым инвестором и потребителем выступает именно государство. Для России развитие в это направление также имеет критическое значение. С 2020 по 2024 год в рамках федерального проекта «Цифровые технологии» национальной программы «Цифровая экономика Российской Федерации» была запущена дорожная карта по квантовым вычислениям, а в новом нацпроекте «Экономика данных», стартовавшем в этом 2025 году, инициативе «Квантовый вызов», этим технологиям уделяется повышенное внимание, включая развитие квантовых вычислений и квантовых коммуникаций, что подчеркивает серьезность государственных амбиций в этой области. Направление квантовой коммуникации стало одним из 5 высокотехнологических направлений, развитием которых правительство Российской Федерации занимается совместно с государственными корпорациями, госкомпаниями и коммерческими организациями. Таким образом, квантовые коммуникации – это одновременно и связь, криптография, и информационная безопасность. К 2025 году мощность отечественного квантового компьютера достигла 50 кубитов, а согласно целям, поставленным в экономике данных, мы планируем выйти на цифру 300 кубитов к 2030 году. К исследованиям привлечено более 15 вузов и более 600 ученых. Мы высоко оцениваем ведущую в МСЭ, прежде всего в секторе стандартизации электросвязи в целях создания глобальной архитектуры квантовых коммуникаций. В настоящее время Международный союз электросвязи располагает набором из 40 стандартов для квантовых технологий, в основном ориентированных на квантовое распределение ключей, охватывающих аспекты сетей, безопасности и сигнализации. Еще более 30 стандартов находятся в стадии разработки. Работа Союза электросвязи по стандартизации квантовых информационных технологий способствует ее глобальному развитию. Российская Федерация активно поддерживает инициативу по проведению таких работ в Союзе электросвязи. При нашей поддержке в сентябре 2019 года создана оперативная группа, которая предоставила платформу для совместной работы над аспектами квантовых информационных технологий для сетей на этапе предстандартизации. Сопредседателем данной группы был представитель Российской Федерации. Всемирная ассамблея по стандартизации электросвязи в 2024 году в городе Нью-Дели поручила продолжить изучение постквантовой криптографии, признала, что надежная волоконно-оптическая инфраструктура, включая сети оптоволокно до дома, может стать основой для внедрения квантовой связи. Мы рассматриваем данное мероприятие как важный вклад в укрепление международного сотрудничества, гармонизацию усилий в сфере квантовых технологий. Желаем всем участникам плодотворной работы и конструктивного диалога. Спасибо.
Thank you for those remarks, Mr. Shoytov, and for taking the time to join us today. Moving forward, we will now hear remarks from Mr. Vasiliev, and the rest of the episode will be conducted in English for those of us watching the live stream.
Благодарю вас. Уважаемые коллеги, от имени Постоянного представительства Российской Федерации при отделении ООН и других международных организаций в Женеве рад приветствовать участников вебинара, посвященного актуальной теме развития квантовых технологий в России. Весьма признательны сотрудникам Международного союза электросвязи, Российской академии наук, Министерства цифрового развития, связи и массовых коммуникаций Российской Федерации за организацию вебинара. Надеемся, что это мероприятие, которое проходит в рамках празднования Международного года квантовой науки и технологий, будет способствовать укреплению и наращиванию многостороннего научно-технического взаимодействия в интересах устойчивого развития и процветания всех стран. Развитие квантовой физики переживает вторую революцию, которая связана с раскрытием прикладного потенциала результатов научных исследований, в частности при создании нового поколения суперкомпьютеров, высокоточных измерительных систем для навигации, защищенных каналов связи. Ключевая роль здесь принадлежит МСЭ, как спецучреждению ООН в области электросвязи, которое разрабатывает международные стандарты, обеспечивающие функциональную совместимость и надежность разных информационно-коммуникационных технологий, в том числе квантовых. Отрадно, что российские эксперты вносят весомый вклад в эти усилия. Развитие квантовых технологий в нашей стране носит системный характер. Создан и успешно функционирует ионный 50-кубитный квантовый компьютер. Ведутся работы над повышением точности воспроизводимых вычислительных операций. Активно развивается постквантовая криптография. В условиях стремительной цифровой трансформации и формирования нового технологического уклада Россия последовательно выступает за доверительный, профессиональный диалог, направленный на выработку жизнеспособных решений таких насущных задач, как преодоление растущего технологического неравенства, расширение доступа к передовым технологиям и исследовательской инфраструктуре, деполитизация работы международных научно-технических площадок. Мы убеждены, что технологический прогресс должен объединять страны, а не служить инструментом дискриминации и геополитического соперничества. Желаю участникам вебинара интересной и плодотворной дискуссии. Благодарю за внимание.
Thank you, Mr. Vasiliev, on those opening remarks, especially on the use of the technology for the benefit of the global good. And now we're going to move on back to Mr. Alexander Gorbatsevich, who will give a presentation on the national strategy in Russia.
Thank you very much. Please, the first slide. Первый. Dear colleagues, dear participants of the webinar, the general structure of this field, quantum technologies in Russian Federation, is presented in this slide. You can see it on your screens. We have two main partners in this field: government and business and industrial partner. Can you? No. Не надо мне следующий. Убрать можете? Убрать. Убрать. Just a minute, please. Правую самую. Well, okay. So you can see a government contour and business and industrial contour. In the government contour, three main ministries are engaged in this field. Yes, thank you. It's much better. Ministry of Science and Education, Ministry of Industry and Trade, and Ministry of Digital Development and Telecommunications. All the expertise is conducted by the Russian Academy of Sciences, and this all performed in coordination with business and industrial partners. As a result, two roadmaps has been formed, and they are organized in one federal project, data economy. The first roadmap is a roadmap for quantum computations, and the second roadmap for quantum communications. These fields are financed on a parity basis by the government and by industrial companies and corporations. Hence, these companies and corporations are responsible for the results of these roadmaps. For roadmap of quantum technology, the government, the partner for the government, the main partner is the State Atomic Energy Corporation, Rosatom. And for roadmap for quantum communications, the responsible company is a Russian railway company. Later I'll comment why Russian railway is close to this topic. And these two roadmaps are conducted by a number of institutions, universities, startups, units, which form the community, so-called quantum community of Russian federations. They work in close collaboration. Startups are formed on the basis of research universities or research institutes, so it's a real very effective research and development environment. And now we'll start to the details, and we'll go to the details as probably the main part. Yes. Without delay, I'll transfer to part one of our webinar, National Quantum Strategy and Scientific Achievements, and we'll talk in details about roadmaps, the development of quantum technologies. These two roadmaps are depicted here on this slide. And as I have mentioned, the corporation which is responsible for roadmap for quantum computation is State Atomic Energy Corporation, or Rosatom. Please, second slide. Second slide. Второй слайд. Ну, второй теперь. Да, второй. Да. Нет. Нет. Я, Анастасия, вам прислал слайд. Один слайд. Я прислал 2 слайда. Нет, значит, ладно, уберите. Нет, ладно, покажите 4-го слайда. Значит, нет, вернитесь к предыдущему. Вот это, да. Все. 4-й. Thank you. Here is a general structure of the main platforms which are under research study in the Russian universities. There are ions, atoms, superconductors, and photons. Below are the list of below you can see the number of qubits which have been already achieved, are planned to be achieved in the nearest future. So these are the main platforms which are under study all over the world, and the Russian Federation, especially the State Atomic Energy Corporation, Rosatom, is engaged in all these 4 directions. Следующий, презентацию следующую. Нет. Well, гасить все. Окей. Значит, окей. These large projects are aimed to achieving some performance indicators, and these performance indicators are special for quantum computations and for quantum communications. And as I have mentioned before, quantum communication and the relation of quantum communication to Russian railway company is not so evident. But you see, Russian railway company is the owner of a large network of fiber optic network along the railway road of Russian Federation. And this network, the length of this network is more than 7,000 kilometers. So now all this network is developed to become a quantum network. We have segments of 100 kilometers, which are divided by some stations where the transformation from quantum to classical and backward to quantum information is performed. And so it covers the whole territory of Russian Federation. The most urgent topic is to change, to replace these transformation points to fully quantum connectors. And these two main directions will be presented in the forthcoming presentations. Quantum computation based on ion traps, which will be delivered by Nikolai Kolachevsky. The fundamental problem of quantum memory, which is necessary to replace quantum interconnects, to replace quantum classical interconnects by purely quantum interconnects, will be discussed by Alexey Kalachev, and the forthcoming part of new roadmap for quantum sensors will be presented by Alexey Akimov. Thank you.
Thank you, Mr. Gorbatsevich, for that introduction to the strategy. And now we're going to move on to the session on the scientific developments that are currently happening in Russia. And so we're going to start with Nikolai Kolachevsky, who is at the Russian Academy of Sciences, and he is going to speak on the development of ion trap computers in Russia.
Thank you very much for introduction. I'll try to now share the window. Okay, share. I'm partly will give this talk as a representative of Rosatom Corporation, governmental, and the Rosatom Corporation, as academician Gorbatsevich told, is responsible for two roadmaps. Is quantum computation roadmap, which started in 2020, and the quantum sensing roadmap, which will start in 2026. But I'm presenting here some structure and some results within the quantum computation roadmap. We all know that quantum computation today is a promptly developing field. A lot of huge companies like IBM, Google, Quantinuum, and other corporations rapidly develop their alternative computational way to classical computation, and it's envisioned in 2030 that quantum computation will contribute to high productive computations and solving or contributing to solution of many tasks which is vital today, like optimization tasks and drugs production and logistics and some ecology problems. So in addition, of course, it's a lot of physical problems behind, like new materials, new molecules, folding of different type of complex molecules and so on. So, of course, most of these ideas yet are not really major, but what we are looking for is scalable approaches. So we now test sometimes on 10, 20, 30, 100 qubits, some algorithms which with development of quantum computers will scale up and will contribute to these important tasks. We see that the world is rapidly developing. Over 10 years, it's a huge progress, and there are different platforms which are already announced, like superconductors, ions, atoms, and photons have their own leaders and their own roadmaps, basically, for development. And we see that one of the leading platform is superconducting platform. Basically, the Nobel Prize of this year for physics was given for basics of this computation and Josephson effects. They possess today the computers up to 1,000 qubits with working horse like IBM processors of 127, 150 qubits with high fidelity. Already logical qubits are in play, and the plans, as you see here, is very ambitious. For ions, there are also leaders in the field. For example, the American company Quantinuum recently announced a 96 qubit system based on chip technology with very high fidelity of 1 and 2 qubit operations, and already tried to solve some practical algorithms with JP Morgan, for example. Atoms also show immense progress, thousands of qubits already announced in continuous operation in Harvard Group and some kind of commercial companies. So you see that the world's background is very vivid, and it's interesting to know how Russia evolves and develops its own quantum program in this scale. Over last 5 years, I would say that we did very intensive and successful progress from basically nothing. In 2020, we generally had mostly theoretical research in the field of quantum computation, but in 2025-26, we already have 4 platforms which are well developed, up to 50 qubits with a reasonable 1 and 2 qubit fidelities, and many algorithms which are already tested on hardware, and many algorithms which are developed on paper and tried on emulators. Although you can see on the right part of the slide that there are investments which different countries invested in different quantum programs, and we see that Russia is not the leader in this field, although we are quite, from my point of view, from my opinion, quite successful in developing our own quantum programs. So, of course, China and the United States, they are the leaders, and they have very promptly and efficiently developing technologies and teams. So we try to collaborate in spite of all today's frictions. Basically, the first part of Russian quantum project, which was for last 5 years, was mainly focused on developing of basic hardware and trying to play with some algorithms and on different platforms to just probe where it works, how it works, what algorithms may be scalable and interesting. But the goal of the 2030 is quite different. So we already focus on practical applications of quantum computation, and governmental corporation Rosatom offers a very fruitful playground for this goal, because there are a lot of organizations, industrial, IT, and so on, which plan to implement some basics of quantum computation on their side. Of course, there's a strong educational program and cloud software which for users. So we really try to push forward these ecosystems for the future, and 2030 is kind of attractive point to achieve next stage in application of quantum computation. This slide has been already shown, and it demonstrates some part of quantum activities in quantum computation in Russia. So it's ion platform, atomic platform, superconductor platform, and photon platform. I will not comment on it. It's quite clear for reading. I will give in the last time a few words about ion platform, which I personally is involved in development. It's my field of scientific interest, and I can comment a few words about it. Still, it's interesting also to look in the competition, world's competition, from another point of view. So we know the competition in the number of qubits, which was important till basically recent years, and also one has to take into account the quality of operation. Basically, the 2-qubit operation error, which is critical for number of operations which one can perform on quantum computer. And we can see that the right up area is attractive because the quantum so-called supremacy probably appears in this blue square. And different platforms, different approaches try to reach this area. For example, these green points are achievements of American struggle companies and institutes. Up is quantum atomic platform. To the right, we see ionic platform. In the middle, you see IBM and so on. So it's very strong success, and it goes forward. Red points represent Chinese achievements, blue points are Russian, so we are visible on this plot. Of course, we are not in the first row, but still we go forward, and I think that the cooperation with different countries, with different scientific groups will help all fields to go forward and at the end reach practical applicability of quantum computation. Inside Russia, we have also a huge cooperation of different institutes. You see that about 80% of universities and research institutes are integrated in this program. 19 leading Russian universities are co-executors of the roadmap, and more than 600 engineers and scientists are involved in this development. We have tight contacts with many countries as today. I mean, as indicated in this slide, we have cooperation with about 75 laboratories all over the world, and about 30% of these connections are active. So we exchange students, we organize scientific seminars, and so on. So traveling visitors, and of course we are interested, and we wish that this community will grow up in spite of all the problems which appear today. As for example, I will give a few slides about 50-qubit ion computer, which is QUDIT architecture. So each ion, which has the dots on the top of this slide, encodes 4 levels or 2 qubits. So it's 2 qubit encoded in each ion. And we have quite decent characteristics of the systems, which are plotted here in the slide. And we also access this array with a cloud platform and start algorithms, as shown also here. So it's not very complex algorithm typically, but we tried quite a lot different approaches. For example, quantum chemistry with modeling of lithium hydride molecule, some machine learning tasks with lung diseases, with number recognition, the entangled states, and also I think, which is one of the leading fields where we try to push forward, is optimization algorithms, quantum optimization algorithms, because it really easily maps on quantum computer architecture. It's scalable, and on the other hand, it's e-zinc model, which easily maps on practical tasks like logistics optimization and so on. Together with practical tasks, I find personally that this is a great scientific field. It's a very nice quantum science which is behind this quantum computation, and it really unifies scientists from all over the world. And we are proud that many interesting and important scientific papers are published by Russian teams and by joint teams. For example, this is one of our recent papers in Physics Letters, where we did scalable improvement of TOEFL gate with big number of ions involved for Grover algorithms optimization. And this is a world record, and our young students and PhD students are really push forward this field, and they really rave for good publications and visibility, international visibility. And of course, we have a nice advantage within the Rosatom system that, as I mentioned in the beginning, that we can implement our ideas in some practical tasks. And there are recent use that Rosatom, for the first time, used a 50-qubit quantum computer to solve the problem of heat transfer as a part of a PRORIF the nuclear power plant project. So it's of course a simple task. It can be solved on standard regular computer, but of course making possible to solve it also with quantum computer adds some interest, and it's scalable, which means that if we have better and more qubits, the task at some point may be advantageable for quantum computers. So I thank you for attention. Of course, it's a very brief scope of our activities in frames of the roadmap quantum computation, but I hope other speakers will give more details on this. Thank you.
Thank you, Nikolay, for that detailed overview of the progress across multiple quantum hardware modalities, and especially the insight into the ion trap architecture. I'm curious if you would be able to elaborate a bit on how you see the scalability of the ion trap platform relative to the other approaches you mentioned, especially forward.
Yeah, thank you for the question. It looks like that, of course, it's one of our, for ion platform is one of the difficulties indeed, but comparing and think about progress with chip trap ion architecture like Continuum shows, we also do today this research on trapping ions on flat ion traps. I think this is solvable. So thousands of qubits can be achievable by this architecture, although, of course, it seems to be inferior to, for example, atomic platform. Seems to be. Although, thank you, it's a good question.
No, thank you for that explanation. You also mentioned that Rosatom recently used a 50-qubit system for a heat transfer problem. I'm curious, from your perspective, what other applications do you think are most viable in the near future, or will be most focused on areas like chemistry, optimization, machine learning, any of these that are priorities?
I think there are two maybe areas where we try to focus. Optimization is maybe in highest priority, so it can concern finance, also it can concern logistics and so on, because it really easily and readily mapped on quantum computer architecture. Another area which I think the quantum computers will be fruitful are material how to say, simulation, because typically material quantum systems are complex quantum systems like magnetics, superconductors, Cooper pairs, strong correlations, and quantum computer is very strong in calculating this or simulating these correlations. So I think this field of simulating physical processes, which is important for practical, like for example, high temperature superconductivity, something like that. For example, D-Wave already solves kind of that problems with some signs of supremacy, I would say. That's also the way where one has to go. Thank you.
Absolutely. Thank you so much, Nikolai. Great presentation. Moving on to the next presentation on scientific development, we're going to hear from Alexey Kalishev, who is going to share more about quantum memory. Welcome, Alexey.
Thank you very much for introduction. Let me share my screen. Not here. Okay. Okay. Is it okay with my presentation?
Yes, looks great.
Thank you very much. So I'm going to talk about fundamental problems of quantum communications related to quantum memories, quantum repeaters. But first, let me start by making some comments on the quantum communication roadmap. In 2019, the government of Russian Federation designated joint stock company Russian Railways as a leading enterprise, which is responsible for development of high-tech field quantum communications in our country. And main goals of this roadmap is to create quantum communications infrastructure, to achieve technological sovereignty in the field of quantum networks, and to assure the development of quantum communication ecosystem. In particular, quantum communication infrastructure includes backbone quantum network, regional quantum networks that include both optical fiber and atmospheric communication channels, and space segment of quantum communication network. And special attention is given to developing quantum systems between unmanned vehicles and to developing interfaces for users with portable devices. And it should be noted that all scientific and technological projects are prepared and launched by Quantum Communication Section of Scientific and Technical Council of Joint Stock Company. This allows one to take into account positions of all participants in the ecosystem of quantum communications and develop a consolidated position. The section includes four expert groups: network technologies, space quantum communication systems, emerging technologies, and user systems and component base. In particular, fundamental projects that I'm going to talk about are considered in the third group. And the topics of them are quantum memories, quantum repeaters, device-independent quantum cryptography, and quantum networks. An important part of the developing quantum communication infrastructure is inter-university quantum network. At the moment, we have a backbone quantum network connecting St. Petersburg, Moscow, Nizhny Novgorod, Kazan, Samara. And inter-university quantum network is developing on the basis of local networks appearing in these cities. And in 2024, a consortium of 6 universities and 1 academic institution was organized in order to develop such a network in the nearest future. And it should be noted that the inter-university quantum network is planned to be used not only for quantum key distribution via trusted nodes, but also as a test bed for promising quantum communication solutions, including fundamental research. And now let me discuss some fundamental topics of research in the field of quantum communications. One of the most important problems in the development of quantum technologies is the scalability of quantum networks in order to transmit quantum information over long distances. And solving this problem will make it possible to create quantum internet, which is expected to significantly expand the capabilities of quantum communications, quantum computing, and also quantum measurements. Among the applications of extended quantum networks are device-independent quantum cryptography, blind and distributed quantum computing, quantum clock synchronization, distributed quantum measurement, and longer baseline telescope. And the key point of these applications is the distribution of entangled quantum states between remote nodes. However, due to the losses in quantum channels, direct transmission of quantum states over long distances is almost impossible. Therefore, the quantum communication range is limited to distances of the order of 100 kilometers. It's important to know that quantum networks with trusted nodes, which are actively developing today, are not suitable for the distribution of quantum states, since in trusted nodes, quantum information is converted into classical information, which allows implementation only secret key distribution. And there are two promising approaches to building large-scale quantum networks. The first one is to use quantum satellites, and the second one is to use quantum repeater. The former is obviously useful for intercontinental distances, but in this case, communication rates depend strongly on weather conditions in different places. The second approach is better suited for smaller distances of the order of 1,030 kilometers, but allows a stable continuous quantum communication using optical fiber channels. And the main task of quantum repeater is to distribute an entangled state between distant nodes containing quantum memories with the rate greater than the direct transmission limit. And the resulting entangled state forms a basic resource for long-distance global quantum communication. And without going into details, the key ingredient of quantum repeater is optical quantum memory, which can be defined as a variable delay line for quantum states of the electromagnetic field. And for quantum repeaters, it's necessary to store information for time intervals longer than propagation times of light through the total communication channel, which exceeds hundreds of milliseconds. In other words, we need long-lived quantum memory, which also have a high efficiency. And such memory devices have yet to be developed. Therefore, this is a topic of active fundamental research. And there are centers in Russia which are actively working in this field related to quantum memory, quantum repeater. I would like to mention Gaponov-Grechov Institute of Applied Physics of the Russian Academy of Sciences, where experiments on quantum memory doing. And then National Research Technical University, where quantum memory studied both experimentally and theoretically, and Kazan Scientific Center of Russian Academy of Sciences, where theory of quantum memory is developed and narrowband single and two photon sources compatible with quantum memory devices are developed. And in particular, as part of the quantum communication roadmap, Kazan Scientific Center and Institute of Applied Physics have been implementing a joint project which is aimed at demonstrating an elementary segment of quantum repeater. In our case, we develop a system of compatible narrowband two photon sources and quantum memories, two quantum memories. And during the project, quantum memories based on YSO crystal with erbium ions were developed with capable of storing and retrieval of polarization states of single photons with efficiency 25%. And two photon sources sources of entangled two photon states based on spontaneous parametric down conversion in a cavity were developed with a line width of photons less than 10 megahertz. So these sources are compatible with developed quantum memories. We also found useful to use two resonant optical parametric oscillators with cavity finesse not equal for signal and idle fields. And with that, we observed photon echo signals in our memory devices. So we observed storage and retrieval of SPDC photons in such memories. And finally, we combined two sources of entangled photons and two quantum memory devices, and just finished the test in our setup. The results have yet to be improved, but already demonstrate the possibility of entanglement swapping in this system. I just mentioned that typical four-fold coincidence rate is about 10 to minus 3 Hertz, which means that the measurements take quite a lot of time in this way. So in conclusion, I would like to say that implementation of quantum repeaters and bringing this technology to commercial level is an urgent and most fundamental task in the field of quantum communications. And the practical significance of this technology is determined by the possibility of scaling quantum networks using untrusted nodes. And the key technology in this field is creating quantum memories, long-lived quantum memories. And demonstrating an elementary segment of quantum repeater is an urgent topic of research in many countries, as well as in Russia. Thank you very much for your attention.
Thank you, Alexei, for that presentation on the quantum communication roadmap, as well as highlighting the fundamental role of long-lived quantum memory. I'm curious from your perspective, since we know that we need to be able to store quantum states for a longer period of time, what do you see as the most significant physical or engineering bottlenecks, and which approaches appear the most promising?
Of course, it's necessary to find appropriate materials which allow implementation of storage simultaneously with long coherence times, long storage time, and high efficiency. And from this point of view, I think crystals doped by ray of science, for example, are the best at the moment, very promising materials for that, because in such materials it was demonstrated coherence time of the order of 10 hours, which is very impressive results. However, efficiency in this case is not very high. So this is, again, this is fundamental research topic, because we have to find optimal conditions to combine in one device, a single device, long storage time and high efficiency. And I think the main task is to find appropriate material and appropriate protocol suited for such material in order to achieve this goal.
Absolutely. Thank you so much for that presentation, Alexei.
Thank you.
Next in our discussion on scientific developments in Russia, I'd like to welcome Alexei Akimov, who will be speaking on quantum sensors on diamond coloring centers.
Thank you so much. Let's see if I will figure this out. Okay. Welcome, everybody. So my colleagues were talking about global things like quantum technology in Russia as a whole and quantum repeaters as a big task. So I would like to be a little bit more focused and talk on only one specific type of quantum sensors based on diamond. And I am really hoping that our moderator is not an avatar and she will appreciate choice of topic. So why quantum sensors and why diamonds? So as you probably know, we can build quantum computers in many systems. There are mentioned ions, there are atoms, quantum dots in silicon and all other platforms. Diamond is one of them. You can use color centers in diamond as a qubits. So this defect in diamond, which eventually can give it a color, they can be treated as a qubits. But one could actually think about why these qubits are not so great, why we're not making millions of qubits already. And the reason is because these qubits are affected by environment, right? There is temperature outside, there is magnetic field, electrical field, tension, all of these factors, they making this operation of these qubits worse. But one could, of course, look at this problem from another point of view and say, look, if I have qubit which is destroyed by, say, some external factor, I can actually use this destruction of a qubit as a measurement of external factor. And one can take different types of qubit in diamond and try to measure different things with it. One of the things we're trying to measure is temperature. And original motivation to measure temperature came from biology, because for biological sensors, it's very important to have something which is non-invasive. You don't really want your sensor to bring harm in your living system, and diamond appears to be nice in this sense. It's chemically and physically inert. It doesn't really affect functions of the cells, so you can really put this little diamond, which could be also made very small, some tens of nanometers, inside the cell itself will be fine. Or you can bring it close to the cell and it would not really disturb operation. So first attempt on making sensor in a diamond was made by Michel group at Harvard, and they demonstrated very nice sensitivity, but the problem was that at that time they were using microwave radiation in order to read out sensor state. And that's not very cool, because if you're using microwave radiation on the frequency of microwave oven, in a power of few watts, you don't really know if your sample was cooked before you measured it or not. And in order to avoid it, my group decided to develop all optical sensors based on a different color center than diamond, and we succeeded in doing so. So we developed a sensor based on germanium vacancy color center and showed that we can measure temperature with sensitivity of about 0.1 degree in a reasonable time, or it could be better if you are ready to wait longer, which operates on a sample, small diamond sample, which, for example, can be placed on a fiber end. There was quite some work on optimizing which exactly fiber to take and how to avoid self-heating and other problems, but today this type of sensors is used in biology inside mice brains to determine if you overheating brains doing some manipulations with them or not. Turns out for quite some research directions that was a problem. So people were sending some pulses to make mice go in certain directions or do something, and on the way were burning their brains without temperature measurement. This is application we already have, but apparently it's not the only one. So once we have this sensor, it appeared that Russian industry, especially energetic companies, energy distributing companies, they are very interested in those, because some transformers, they have quite aggressive temperatures and environment in which not many thermometers survive, but fiber-based diamond thermometer will survive, and they have a lot of letters of interest, so they looking in it and really kind of rushing us to make a product. Now, that's not the only thing you can do with diamond. You can also use diamond to measure magnetic field, and here main motivation again coming from medicine, I would say. There is a procedure called magnetoencephalography, which is scanning of magnetic field activity of the human brain. So whenever we think or doing something like a current happens in our brain, and that produces magnetic field which could be measured. Unfortunately, maybe fortunately, magnetic field which brain produces are very small. So memory, attention, perception, cognition, all of this produces magnetic fields of about 10 femtotesla. So it's tiny fields which are very hard to measure, and today they may be only measured with superconducting detectors, which have to be maintained in a 4 Kelvin and a liquid helium temperature, and helium is getting more and more expensive, so that's quite difficult to use those. Of course, there is strongest signal, which is associated with alpha rhythm of human brains, which is around picotesla, and that's easier to detect, but that's also a bit less informative. So it's interesting to replace this detector with something which doesn't require this low temperature, and it doesn't require liquid helium, and we started to work in this direction. Many other groups started to work in this direction, and we started to think about using nitrogen vacancy color center in diamond, which is apparently is a good magnetometer because of its properties. It appears that this specific color center changes its fluorescence depending on its spin state, and spin state is dependent on magnetic field. So by combination of change of fluorescence and measuring orientation of different spins, you can actually measure magnetic field in this system. In the world, people put in a lot of effort on it. There was theoretical prediction that you can get indeed to the level of femtotesla. It was not yet experimentally achieved, but people got pretty close. So the sensitivity of this magnetometer is already reaching about 70 femtotesla for alternating magnetic field and about a couple hundred femtotesla for DC magnetic field. So it's really getting there, despite the fact that medical application goal is not yet achieved. We're not yet under 10 femtotesla. Once these devices appeared, many companies, startup companies, started to appear around this color center, finding more and more applications. So, for example, if you have electrical circuit and you need to find defect in it, it could be done with magnetic scanning magnetic field sensor, and that's one of the applications people exploring right now. Another one, it turns out magnetic field sensor can help you to analyze different types of tests for human blood and stuff like that if you use it in combination with magnetic particles. And people also using it for finding defects in metallic constructions and for scanning of geological rocks and many other applications these days. In our lab, we are developing a magnetic field sensor based on an INV center, which is mainly oriented on, I would say, application and navigation by magnetic field, but also we're trying to improve quality of a diamond, which we're using for this color center and working a lot with the groups which are growing diamonds. And trying to use our magnetometers not only for some practical applications, but also to study diamond itself. For example, nitrogen is one of impurities which is necessary to have nitrogen vacancy color center, but it's also maybe a source of decoherence, source of the problems inside diamond itself. So it's important to be able to diagnose how much you have and do it precisely and accurately. And we decided to use INV magnetometer itself to measure impurities inside the diamond to control quality of diamond plates we do. And that was quite successful. So we developed this method. We were able to measure many diamonds with it and confirm that on one way it has good correspondence with previously known methods, but also that we actually can improve on quality of measurements and also do measurements locally only in only around in the centers which we're using, but not an entire sample. And unfortunately, diamond samples are not always uniform, so you need to be careful on what you're measuring. Sometimes old methods, they kind of average over used and unused part of the diamonds and given errors. So another possibility is to build rotation sensor. Again, it's done with NV center, a nitrogen vacancy center. And here idea is following. So it turns out that elementary particles, they do have mechanical moment associated with their existence. And this mechanical moment is basically a gyroscope which you can use to measure rotation, much like they do with mechanical gyroscopes for modern ships and stuff like that. Nevertheless, in the quantum mechanics, this gyroscope comes with a magnetic moment. So it turns out it's not only has orbital moment, but also magnetic moment, and therefore it's also sensitive to magnetic field. Luckily enough, it's different ratio of sensitivity to magnetic field for nucleus and for electrons. And for nucleus is much smaller. Therefore, within one color center, we can measure magnetic field on one side using electron spin, and then use nucleus spin to measure rotation and correct for effects of magnetic field using signal of electron spin. And with this simple idea, we were able to build such a sensor. We did a first demonstration and showed that it can see rotation, and now working a lot on improving its size. It's been a quite big experimental setup in the first experiments, and also sensitivity. And one of the ways to improve sensitivity is come back to Alexei Kalachov talk and try to recall about quantum memory. One of the ways of build quantum memory is electromagnetically induced transparency, which is also known for slow light experiments. And that's one of the ways to create basically some kind of superposition state, some kind of coherent state in an atomic system using two light pulses. And that being demonstrated to be used as a memory, but we can use it to create state which is sensitive for rotation by applying not really light pulses, but by applying microwave pulses. And that helps us because the most difficult to make a compact part of our setup is radio frequency control. Fortunately, we need for this manipulation of nuclear spins. If we get rid of it, we will decrease weight of our setup by a factor of 2 at least. And that was done, so we were able to implement this microwave control in nitrogen vacancy color center, and we're able to control nuclear spin and create superposition state with a very high contrast, which is illustrated here. So we now work in further steps and trying to implement this technique into sequence measuring rotation and develop compact sensor based on this approach. Now, that's more or less what we're working on. So it has biological, medical applications. There is a geological application for search of some magnetic metals and other things in the mountains, rotation sensing, important for navigation and other things, temperature measurements in vivo, and brain studies. That's all on agenda. And of course, this is only what we're doing in our group. There are many other groups working in Russia in quantum sensors. We have beautiful projects for atomic-based sensors, for sensors of different gases, for sensors of gravity and acceleration. And those all probably will be represented in a Russian roadmap on a quantum sensing once it will be approved. So with this, I would like to thank you for your attention. Thank you.
Thank you so much, Alexei, for that look into how diamond color centers can be used in quantum sensing. I did have a follow-up question for you, because I do think that anytime we can highlight the significance of potential applications, using quantum technology, I think it's very important. And I really think that this was interesting in terms of how these sensors can offer a non-invasive way to measure temperature inside living systems, and how this can be used in the brain study that you talked about. So I'm curious, for our audience, would you be able to expand a bit more on what kinds of biological or medical questions become more accessible when you can place nanoscale, non-disruptive sensors directly into cells or tissues? Just other areas of study that might be applicable, because this is obviously very, very relevant.
Yeah, so there are many things which could be explored. So one of them is just, like simple heating of the cells. So some different cells may die at different temperatures. And it's sometimes important to monitor what you're actually doing when you're doing some biological research, because some may survive, some may die, and then you have something which looks alive, but not quite alive. Then, of course, there is thermogenetics. So there is ways how you can control neurons using temperature, which actually used in biology by snakes and other animals. So they actually use temperature to activate their neurons, and basically they smell. For example, snakes are hunting by temperature, which actually been proved using diamond color sensors. So that's like been really discovered using this approach, because before that it was not really known. There was different hypotheses, and here we were able to discover them. Then there are fundamental questions on how cells are operating and how power plant called mitochondria works in a cell, and those also could be addressed using local sensors which are implanted inside the cell. And such experiments are underway. So also people trying to see what is happening when cell decided to divide or decided to do something, see how energy actually is transported. That's where the sensors can help. And that's only temperature sensors. Of course, magnetic field sensors can be diagnosed for example, heart disease. Right? Some of the heart diseases are very difficult to diagnose in the early stage, but using magnetic field sensor, you can in principle do it. That's again work in progress. There is no yet something which is in the clinic, but that's principal studies show that that's possible. Right? There are many brain studies which could be done via magnetic field, and magnetoencephalography may be made much more accessible if sensor will not require cryogenic heat. But not there yet, but if we get there, that would be great breakthrough. If there are many diseases which are hidden in our brain, and we can, brain usually knows that we are sick, just not necessarily we know how to extract this information. Right? So that's another application. There are many more. So to not take much more time, I will stop here.
Thank you so much. I feel that quantum, when we speak about quantum, we often computing comes to mind, but people don't necessarily realize that it's already been very critical to the medical field and will continue to be so. So thank you for sharing more about quantum sensing. And thank you to all of our presenters who really elucidated what is happening behind the scenes in terms of scientific development in Russia. It was very, very interesting. And I love that we heard about computing, communications, and sensing. So with that, we're going to move on to our next segment, which will focus primarily on industry and startups. So with that being said, I'd love to go ahead and welcome our first speaker, who is going to be representing Scontel. And I will go ahead and stop my screen so you may share. And this is going to be Gregory Goldsman.
Thank you for introduction. Let me share my presentation. I don't see it. Sorry. Oh, here it is. Okay, thank you for the introduction. In my talk, Superconducting Single Photon Detectors, I will show you how I came from the first scientific paper to the market. And here I have a few pictures. First about first publication, how to count photons by superconducting nanowires, then to the practical detectors on single mode fibers, and then to the nanowire of superconducting detectors, and the last one to the optical chip, to how to count photons on optical waveguide. This is my outline. So next, first observation of SSPD response and first idea of device physics. Here you see two papers. One of them is a theoretical one. We predicted this phenomena in superconductivity. And second one, experimental paper. In this paper, we see that superconducting nanowire can count photons in the optical range and also in the infrared. First, we started with superconducting material. This is ultra-thin superconducting niobium nitride film. This is actually unique material for sensitive and fast terahertz and infrared detectors and mixers. Here in this microscope picture, you see that on the substrate, we have several atomic layers of our niobium nitride. This is good quality superconductor. And what I would like to mention that superconducting transition, TC, is about 10 Kelvin. But what is the most important? This is actually superconducting critical current density in the film and then in the nanowire. This is 10 million ampere per centimeter square. So this is very strong superconductor. Actually, before count photons, we started with this device as a predecessor of SSPD. This is hot electron bolometer. This is two-terminal devices as a mixer for terahertz range. And this is just one of a slide about that. It was space qualified devices. And this mixer in bands 6 and 7 of Hi-Fi instrument for 1.4 to 1.9 terahertz on Herschel Space Observatory launch in May 2009 with 2.5 cubic meters of liquid helium. So our devices was in space during 4 years. So then I would like to show clean room facilities to fabricate such devices, but probably I don't need to mention long time on that. So we can fabricate superconducting devices. And then actually from the first paper in 3 years, we came to the market with these devices. It was actually 20 years ago. And now in practical single photon receivers based on this SNSPD for 32 channel single photon receiving system, we have quantum efficiency about 90% and 1.5 micron jitter 20 picosecond, maximum count rate 100 megahertz, and dark count rate about 1 second or even less. So this is unique devices. But actually, we have Crea cooler, and this system is not so small. But anyway, these devices are the best in performance. And what is the most important is that we can count photons actually in the middle infrared, not only in the near infrared. This is first application of the devices. Actually, it was also about 20 years ago. In the first application, we saw that actually there's not only very good devices, but also we have a market for that. So that time it was a problem to see in big CMOS circuits for device debug that if couple of transistor switches from one point to another point, there is a small current through two channels, and through the silicon substrate, it is possible to see several photons and see bad transistors and some problem in the circuits. Next, I would like to mention this also breaks through to switch from devices on single mode fiber to the optical chip. This is our first paper together with our colleagues in the United States in Yale University, published actually 13 years ago. In the optical waveguide, we have our nanowire, and what was good, this is coupling of the light in the waveguide was very good. Actually, in the very first paper, we saw that quantum efficiency is about 90%. And so now we see that every quantum optical circuits on chip, the only technology to count photons, this is superconducting single photon detectors. So this waveguide and superconducting nanostrip looks like that with two contacts. So we can fabricate a lot of devices like that on a substrate and test every of them to optimize all that. So next important point was to switch from nanowire to the microwire. This is important because to fabricate nanowires we need electron beam lithography, but for microwire we don't need that. We need just conventional optical photolithography, and in the technology it is much easier. So here there is a first theoretical paper by Denis Vodolazov and Zotova. In this paper, we saw that they predict that even a several micron wide dirty superconducting bridge is able to detect a single near-infrared or optical photon if its critical current exceeds 70% of the pairing current. So for technology, it was necessary to fabricate film and wires with so high critical current. In this experimental paper, we have shown that this is possible. In the first paper, our typical sample was microstrip constriction type microbridge, and with 2 microns wide strip, and we see that critical current is also very close to the pairing current, and we see that this device can count photons. In this paper, we show that devices 1 micron wide can be very long, like 75 micron long, and such device is a very good single photon detector, can work in the near infrared with such wavelengths, and this saturation from bias current means that we have 100% efficiency in the device, inside the device. Next, on the way to quantum computing based on quantum photonic integrated circuits, we need to fabricate tens or even hundreds of devices. Here we have 64 detectors, directional couplers, and also waveguides with different lengths. So we see that for quantum computer based on photons, this is actually very important. Another applications is quantum cryptography, quantum key distribution. Here there is one of the papers we published together with Chinese colleagues. 3 years ago, it was a record of for the range of quantum key distribution over a fiber communication line. That time it was 830 kilometer fiber. But now our colleagues with our devices switched to the 1,000 kilometers. So devices, superconducting devices, are very useful for quantum communications all over the world. And the last paper I would like to show, this is development of photonic integration circuits for QKD systems. In this paper with our German colleagues, published in 2022, we show that it is possible to have more or less everything on a chip. And now I would like to finish. Thank you for your attention. Thanks.
Thank you, Gregory, for that presentation, especially on single photon detectors and why they're critical to a lot of our more sensitive technologies, such as quantum communication, sensing, and a lot of different technologies within space that we rely on today. And so for our broader audience that may not be as familiar with this technology, I'd love to hear more on your perspective on why detecting single photons is so important, especially with speed and sensitivity, and what other applications become possible only when we have quality detectors with this level of performance.
Thank you for your question. Actually, I can say that if I take a list of our customers, that's about 1,000 of customers all over the world. So I can see that there is, yes, QKD, this is actually biology and medicine, and a lot of fields of scientific researchers. Actually, this photons, single photon detectors, first how the technology was long time ago, and then semiconductor devices, and we came with superconductivity in this field actually 20 years ago. So this is new technology, but I believe that this is the most powerful one. Thank you.
Thank you, Gregory, and thank you for telling us more about the technology that Scontel is currently focused on. And with that, I'd love to welcome our next speaker in the industry panel, which will be Igor Pavlov from Qrate. So welcome, Igor.
Good afternoon, ladies and gentlemen. My name is Igor Pavlov. I'm CTO in Qrate. Our company specializes on the development and production of quantum key distribution systems. Qrate is a research and manufacturing company founded in 2015. We design and produce complete hardware and software solutions for information security using quantum key distribution technology. Our work focuses on two main areas: quantum communications and quantum sensing. We cover a full technological cycle from basic scientific researches to serial production of equipment. Since our foundation, we have built a strong team with 73 employees and including 10 PhD holders. Now we have all licenses from Russian government to create cryptographic devices and cryptographic device. Okay. Дальше. Следующий слайд.
Презентация видна?
Yes, we can see it. We definitely can see it.
Я не расслышал. Презентацию видите?
Да.
It's just
Спасибо.
single slides.
Листать положение.
Не работает?
Да?
So we can see the presentation. It's on a slide with Gazprom Bank and years of foundation of the company and all these things. Key areas of operation.
Yes, now it works.
Okay. Our product line includes 5 main solutions. The first one is QKD 320. This our flagship quantum key distribution system. Назад, на 2 слайда. Еще? Yes, thank you. It relies BB84 decoy state protocol and works on distance up to 100 kilometers, and key generation speed is about 40 kilobits per second. Second product is QKD Mini. It's miniature transmitter of quantum key distribution system. It's full compatible with QKD 312, but designed to minimize size and costs. Maximum distance is about 50 kilometers and the key generation speed about 10 kilobits per second. Third, our project is quantum number generator, QHouse. It generates quantum randomness at 1 gigabit per second and can give output randomness about 2.5 gigabit per second. And fourth, our solution is a single photon detector. It's semiconductor, based on semiconductor diode. It has good quantum efficiency for semiconductor SPDs, adjustable dead time, and high and low noise. Next. Okay. And additional, we have QLab, our fifth solution. And it's an educational complex of quantum communications and photonics. QLab used for teaching quantum optics, information security, and programming, and for conducting scientific experiments in the universities. It's a key infrastructure element in major professional competitions in Russia, such as atom skills, digital skills, high-tech, and professionals. Today, QLab plays an important role in preparing specialists in the field of quantum technologies and educational institutions. Since 2016, Curate carried numerous of pilot projects with major companies and government organizations. The list of these pilots you can see on the slide. Protecting data centers with QKD. One of the key areas when QKD is highly effective is data center protection. Traditional cryptographic systems often use the same key for a long period, such as 1 year. With QKD, keys are updated continuously, reducing the load on each key and significantly lowering the risk of hacking. Our systems can be installed on the top of existing telecom infrastructure, requiring only dark fiber to operate. We support multiple network topologies, such as point-to-point, star, chain, and ring. In 2021, we launched first inter-university quantum network connecting campus of MISIS and MTUSI. Network includes 5 nodes and have open architecture, allowing universities, research institutes, industrial partners, and government agencies to participate. The configuration of the communication channel follows the standards used in industrial networks. Quantum keys are distributed at 30 kilobits per second, this project demonstrates that quantum networks can be deployed today in a real-world infrastructure. Protecting video conferencing systems. And not only video conference, all corporation communications such as video conferencing, messengers, and mail. We successfully demonstrated the protection of video conferencing using QKD, quantum key distribution. Together with Rosatom and Rostelecom, we set up optical communication lines and showed encrypted video calls protected by quantum keys. This technology was present at major international forums and even demonstrated to the presidents of Russian Federation. The QKD 320 system is compatible with existing corporate encryptors, allowing organizations to make their security stronger without replacing existing infrastructure. Integration quantum key distribution system in the enterprise infrastructure. We made MVP with NFC card to demonstrate that quantum key distribution can be integrated in enterprise systems. This slide shows a simple workflow. Quantum key is generated by QKD system, then a key transmitted to administrator's workstation, and then it's recorded on a smart card, an NFC card. The card is used to transfer the session key to a smartphone. The messenger on the smartphone is protected using the quantum key quantum session key. This approach allows organizations to secure their communication tools using QKD without changing their daily workflow. Another step is to protect access control system. QKD also enhances the security of access control system. Idea is the same as on previous slide, but you can protect your access control, and you can give quantum key to the card when employee came into the office. Protecting self-driving transport. In 2021, we carried a project with Innopolis University to protect unmanned vehicle control systems. A stable 4G connection channel was created between vehicle and data center, protected by encryptions that used quantum symmetric keys. Quantum keys were distributed through an optical channel during vehicle charging. We achieved a key rate of 40 kilobits per second, and this project shows how QKD can support the future of intelligent transport and secure autonomous mobility. Thank you. If you have a question.
Thank you so much for that presentation, Igor. This was really informative to hear more about the development in QKD. So really curious to hear a bit more from how is Qrate supporting clients in the transition to quantum safe security in that way? Could you speak more to the services from that perspective?
Can you repeat the question, please?
Yeah, so I'm curious, is Qrate currently working with perhaps different clients or even maybe any sort of experimental type POCs to help implement QKD or any, are there any QKD testbeds that they're actively working on? I know there was talk about an inter-university QKD testbed earlier. Is Qrate involved in that, or do they have another type of real-world implementation?
QKD have a special implementation, and most of these implementations I showed in my slides. And now market of quantum key distribution systems in Russia is only starts up, and nowadays in Russia there is only one customer of quantum key distribution system. It's Russian railway company that builds quantum networks, and we're in contact with them, and they know our possibilities and possibilities of our equipment.
Awesome. Thank you so much. Thank you again, Igor. Love the presentation. And moving forward in our industry and startup focus, we're now going to hear from Anton Kozubov, who is head of advanced R&D at Smarts Quant Telecom. So welcome, Anton.
Thank you very much for the presentation. Here is my presentation I'd like to show you today. So I hope you see it now. And I'd like to share our experience, how we transfer the knowledge from the research areas to the industrial deployment. So talking about our company, Smart Quant Telecom, it's quite a big company in Russia, I guess, and we are mostly focused on the development of the quantum backbone network, which is a part of the quantum communication roadmap, which was told about today a lot of times on the infrastructure of the Russian railways. And of course, we also provide full cycle of the scientific research and applied development. So as I said already, we are focusing mostly on the quantum key distribution system. So the main product that you can see here is the quantum key distribution system that is usually used for quantum backbone networks. But also we provide different component base for quantum and optical technologies, such as single photon detectors, amplitude and phase modulators, and also random number generators. So speaking our research and development structure, of course, we have both fundamental and applied research. Fundamental research is really necessary to open the gate to some new technologies and new possible products, and applied research we usually use for different kind of upgrades and continuous developing of our existing products. And the main idea of our research is to collaborating with our key partners, which are different universities, such as ITMO University or Mathematical University of Russian Academy of Science. And of course, we have also different partners in the information security companies, which are presented here. So we are working with them together and develop different type of projects. So to be more clear, I'd like to show the example that will, I hope, represent how we transfer the knowledge from the fundamental research to the industrial deployment. So the first example that I can provide here is that we had pretty fundamental research in quantum optics. And of course, when you're doing such kind of research, you expect to obtain the fundamental results, and we already did it, such as new algebra of quadratic superapparatus and the dynamic evaluation of the quantum states in a fiber channel. But of course, thanks to that, we had a new opportunity to describe the optical fiber channels in new way for the QKD setups, which helps us to provide it. And it was the basis that transfers from the fundamental results to the some applied research, which we are using still in our products now. Of course, as we develop a new protocol of quantum key distribution in our company with collaboration with the ITMO University, we also have to discuss security analysis from the scratch. And since it was done from the scratch, we have to analyze the different class of attacks. Also, we provided the finite key security estimation. And at the end, we also would like to know how the imperfection of the devices can influence the information leakage of the QKD systems. And since there are a lot of different strategies which can be employed as a eavesdropper to our system, we have to develop and evaluate the countermeasures against these diverse attacks, which are already done here. And it was quite a big research, I guess. But still, we're not focusing only on our QKD system, which is a product in our company. We're also interested in the generalization and the extension of QKD security frameworks, and especially the eavesdropping attacks. And we are still doing it for now and using it in our products. So as soon as I said that we are interested in the influence of impact of real devices on our PKD security, we have to somehow take into account the quantum hacking techniques. At first, we did some research with our partners from different laboratories all over the world. And now we are extending this research, for example, by extending the temperature, temporal, and spectral ranges of the optical radiation, which can influence the optical components in PKD systems. They also provide different new types of attack here, and we develop and evaluate the countermeasures against them, because of course we have to protect our system against what we are considering here. So combining all this research, we have now a final product, I guess, which have some key and unique features, such as a new protocol, which was developed in the collaboration with the ITMO University. It's based on phase-modulated multimode coherent states, and thanks to this kind of protocol, we have some features such as enhanced operational stability with respect to polarization fluctuations, for example, in the quantum channel, and potential capability of multiplexing quantum channels arising from the structure of the states we are using here. Of course, the main thing also about this type of product is that we have to cooperate with our partners from the information security companies. So we are composable with different vendors of encryptors, and I guess it allows us to expose our solutions to the existing infrastructure. And when we are talking about the PKD systems, it's really obvious that we should mention the quantum networks. It's also a big part of our research problems that we are solving. I guess I can divide it into two different parts. The first part is that the PKD networks or quantum networks, which are using trusted nodes, and it's the part of our research which is more applied to the current state of art in our field. But also we are doing research in the non-trusted nodes, such as quantum repeaters, or maybe some new protocols as a twin field QKD protocols. And thanks to that, we have now the development of the quantum backbone network, which is done thanks to the roadmap on quantum communications. And we built more than 5,000 kilometers of this quantum network. Here is the map that shows it. When we are talking about the quantum networks, we also have to talk about the metropolitan networks. And one of the possible solutions for metropolitan networks is continuous variable quantum key distribution systems. We also have a research on it. We're trying to figure out which type of continuous variable quantum key distribution will be more suitable for us, for our networks. And we also analyze the security and developing the protocols for this kind of the systems, and hoping to see them soon, maybe in the global network one day. So when we are talking about the development of our field today, we always talking about the quantum Internet of Things. So what our company doing here is that we have some industrial deployment of QKD system, first backbone quantum network, and variety of different QKD protocols and realization in the part of quantum communication. And we also do some research and some products in the quantum sensors, such as quantum random number generators. It's already some industrial realization of it. And we trying to do some research in quantum optical gyroscopes, quantum interferometry, and quantum magnetometers as well. But of course, I hope that one day we will have a full quantum Internet of Things, which allows us to have a secure and quantum network for all of us around the world. So thank you for your attention. I'd like to answer all your questions if you have them.
Thank you very much, Anton, for that presentation. It's very interesting to hear more about what Smarts Telecom is doing within the industry. As of this time, I don't have a question on this one, but if you would like to provide any more information from your side, please feel free to do so, or else we can close out the industry section.
I guess I'm done.
Thank you so much, Anton. And thank you for all of our presenters on the industry section. This is really important to show how research really turns into real world applications. And it's necessary to have both industry and startup participation to do that. So thank you for our speakers. And now we're going to move on to our next panel. So what we've seen so far is that industry plays this essential role. We know that government is important for collaboration, but ultimately none of that progress is possible without the people making it happen. A strong ecosystem really depends fundamentally on education, on training, and the ability to cultivate specialists across different domains. So with that being said, our next session will focus on workforce, how talent is being developed, how educational institutions are evolving, and how industry, government, and academia can collaborate in order to prepare the next generation of quantum professionals. So with that, I'd love to welcome Professor Sergey Kulik for a discussion on how Russia is approaching quantum workforce development. So welcome. And Professor Kulik, you're currently muted.
Yes, sorry for this. Oh, let me start. Okay. Just a minute. I'm sorry.
No, you're fine.
Okay, can you see my presentation?
Yes, I do currently see your presentation.
Yeah. Okay, so good evening, everybody. So currently I work at Moscow Lomonosov State University. I spend part of my time just by teaching, part of the time for research, but most of the time by doing paperwork. So let me start by saying that in teaching we prefer so-called canonical scheme when in preparing courses, teaching courses, rely significantly on the scientific work that is being carried out in our laboratories. So we actually make research in all parts of all regions or branches of quantum technologies, like quantum computation, like quantum communication, quantum sensors. So we prepare our courses according to these topics. So just briefly, so we contribute a lot to development of quantum communication, and you see some part of our products here. Also, we work actively in quantum computation, doing experiment with 3 platforms, physical platforms like called atoms, traps, and microdipole traps in photonic chips, and also with some impurities in semiconductors. So we have great experience in these fields. Also, we contributed a lot to so-called inter-university quantum network, and Alexey Kalychev has already spoke about this region, so I just skip this slide. But just say a little bit that in Moscow State University we have some local quantum network which contains more than 20 nodes, and length of this total length is more than 50 kilometers right now. Again, I just skip this slide about this inter-university quantum network. So about master's programs that we have in our university, so we see the examples and titles of these courses, like quantum and optical technologies, quantum computing, applied quantum communications, and other. Also, we have some experience by teaching for not only for students in our university, but also for a consortium of universities. And again, you see the examples of these courses over there, like quantum cryptography, physical foundations of quantum computing, introduction to quantum computation, quantum optics, quantum cryptography, and also quantum electronics as well. Again, also have some experience for professional activities. And again, the titles of the courses are put over there. I would like to say that the most important for us part of this teaching is practical training in quantum optics and quantum information science, and later on I will focus on this. Also, we prepare some teaching course for commercial companies, and we see actually some of them large companies and small companies here, like quantum technologies and introduction to quantum communications. And this is, I think, the most important, at least for me, the part of our activity in teaching. So we built about 7 years ago our quantum workshop, and you see again examples of the activity inside this quantum workshop, like quantum key distribution, quantum random number generations, quantum state and process tomography, anti-correlation of photons, and some others. And finally, so I would like to stress that we during many years hold the International School of Quantum Technologies, and you see the names, very famous and beautiful. Our friends actually from many countries like Anton Zeilinger, Arthur Eckert, Philippe Grangier, Mark Safman, Andrew Forbes, and many others who contributed to as a lecture at our international school. So, and the nearest one will be held just in 3 months in Sochi, from 1st to 7 March. So we welcome everybody to join us during this international school. So I'm going to conclusion. So you see just some of them. Personal training process is in a state of despair. Total number of trained specialists is difficult to be estimated. I think it's just in our university, Moscow State University, it's several. Okay, let me say about 100, maybe more. So, and very important aspect of the practical training, which provides opportunities to acquire skills in both physical foundations of quantum technologies and their practical implementation. Thank you very much for your attention.
Thank you very much for that look into some of the training programs that exist for the workforce. I actually have not heard about the international school. I think that's really interesting, especially with the types of guest lecturers that you have. And just for clarity, is that a virtual school that anyone could? Is there an application process? Is it open to everyone? Do they need to be in person? What does that look like?
Actually, we have some problems with communication right now, but in principle, so everybody can apply for this school. So I just demonstrated the website where everybody can use it to apply, to contribute its application. So we welcome to join.
Fantastic. That's great to know. And then you also mentioned that graduates are a rare commodity in Russia. And I'm curious to understand, why do you think that is? Do you see a lot of undergraduates going outside of the country to pursue, to work in other industries or in other countries? Or is it just a matter of not getting them to progress to the graduate level?
Okay, at the moment we have only some students only from Russia, but in principle, so even I think at the moment we have just several students from abroad, but in principle it's possible, of course. And also we have some experience teaching for Chinese, for Indian, and some other southern countries. So in principle it's possible.
Okay, great. And just to understand more about the initiatives that are available for the broader public, beyond the university programs, the quantum workshop that you mentioned in this international school, are there other national or regional initiatives in Russia to introduce quantum concepts into secondary education, so before the university level?
It's hard to answer your question. So at the moment, as I mentioned, so we have only some courses for our countries, but again, we in principle we're ready to do this and cover more countries. Yeah.
Yes, fascinating. And you did mention again that inter-university QKD network, which is really great to see because having some sort of real-world implementation is especially useful in training a workforce. So I'd like to know how effectively do you think Russian industry and academia collaborate on quantum workforce development? Are there other examples of, say, joint laboratories or industry-aligned training or co-ops even to ensure that students get hands-on experience?
Yeah, actually, if we speak about Russia, in the Russia collaboration between Academy of Science, between some industrial organization or educational organization, it's actually work very well. So we have very good collaboration with many organizations, like you said. So I think it works rather effectively.
That's great. And then in terms of this quantum talent gap that we're talking about, are there strategies in place to retain top STEM graduates in Russia or to even attract experienced researchers from outside the country? Can you speak a little bit more about that?
I'm not sure that I understood correctly your question. So could you just clarify what do you want to hear from me?
Yeah, absolutely. So a lot of countries that we've spoken to, really, they mentioned the brain drain that's quite difficult. So they see a lot of undergraduates and graduates even, or postdocs even, that after they finish their education, they're leaving the country and seeking work elsewhere, which is leaving a pretty big talent gap within the countries themselves. So I'm curious how Russia is addressing that. Are there strategies to retain graduates, and are there strategies to attract researchers from outside the country?
Okay, it's hard to answer. I think we again we are open for some countries at least. And as far as I know, in Moscow State University, there are many students coming from south and eastern countries, and they have our education. So we just have to wait a little bit and see what happens in the future.
Absolutely. And then if we look at this at a broader scale, as quantum technology becomes more strategic, is Russia working on building quantum literacy at scale? So including policymakers, other educators, industrial leaders, et cetera, to ensure that there is a common baseline understanding of quantum technologies?
I don't know. So actually, it's hard to answer.
No problem. Well, that's great to see that there are the quantum workshop, there's the inter-university network, and then also the international school, which is really great for providing education within the country as well as outside the country. And so for that, thank you so much for your presentation and for providing more information around what this looks like in terms of workforce and education. And then kind of bringing this entire group back to a closing point as we close the session and reflect on the Quantum World Tour as a whole. There is one theme that is really we've carried across every single country that we've visited, and that's that the understanding that quantum technologies develop within national ecosystems, but their progress really extends beyond national boundaries. So given that this series is very focused on learning from each other's scientific approaches, I'd love to ask a question to each and every one of you or anyone who would like to answer. Given the complexity of the global environment, where do you each see the greatest opportunity for international cooperation in quantum? And whoever would like to answer first, please feel free to take the floor.
Does anybody want to say something?
Sure, but that's a bit hard question to answer. So I think everywhere in the quantum technologies there is a quite some background for collaboration, and we kind of need international minds to unite to bring this promising field to application, right? So we close it to applications and sensors. So there maybe we should start. Quantum communications are already, kind of implementing in life, but I'm sure that some collaboration may help here as well, only maybe it's already on the level of commercial companies. And of course, quantum computing is where we need a lot of collaboration because all qubits we're producing right now, they are not that great yet. We want it to be much better, and idea sharing is very important here.
Absolutely. Absolutely. Thank you.
And probably you are convinced that there is a very large room for attending on the level of graduate student, postgraduate student, PhD students, and the level of research is very high, so it will be very useful.
And the educational level is also very high.
It's well-known traditions of Russian education in natural sciences and physics. They're still alive, and so they were presented in some parts. And concerning the question of Sierra Shuker about going to the reuse, there are a number of programs inside Rosatom State Atomic Energy Corporation, which is responsible for quantum computation program, and very soon it will be responsible for quantum sensor roadmap and program concerning the work with schools, and the audience is very happy when scientists go to school and discuss with them, show there some tricks, some new ideas. They respond to it as some miracle, quantum miracle, and so it's a very attractive trend.
Thank you for that additional feedback. Would anyone else like to answer the question? If not, I can go ahead and wrap the session. Any final?
Well, on the schedule we have now the part panel discussion and answering questions, but thanks to Sierra Shuker, some clarifying questions have been already asked and answered, as I suppose. So maybe some concluding remarks, or maybe anybody wants to ask something. Anybody from the participants of our webinar?
Let me see if we have any questions. So we're currently over time.
Okay.
So I don't know if there's anyone who would like to add any closing remarks, anything that you would like the broader audience to know about the development of the science in Russia or any national strategies, etc. Please feel free to jump in and share them, or else I will go ahead and close.
Okay, I also hope that all the attendants, all the participants, I hope that they at least gain some understanding of the development of quantum technologies in the Russian Federation, and that the doors are open for cooperation and for attending as a part of our teams. Thank you.
Thank you very much. And a really big thank you to all of the organizations and the guests who took the time to participate in today's session. I feel that this episode really provided a clear view into the broad spectrum of scientific activity that's currently happening within the country, showing both the depth of expertise as well as the scale of coordination across institutions. So thank you again to all of our guests. It means a lot for you to take the time to be here. And then for the broader audience, as we conclude not only today's session, but also the final episode of this season of the Quantum World Tour. We'll be back next year, but I do want to take a moment to recognize what the series has achieved. So across continents and very different scientific cultures, we've had a very rare opportunity to see how quantum technologies are developing in real time, with transparency, with technical clarity, and also with the shared understanding that science advances most strongly when knowledge is openly exchanged. And again, kind of coming back to some of the closing remarks that people shared, which is the importance of the knowledge share. So thank you again, and we look forward to revisiting the Quantum World Tour in the new year.
Thank you. Thank you very much.
Thank you.
Thank you. Thank you.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.